In the previous video I was explaining how these 7-segment modules were constructed, and I noticed while I was doing that the digit on the right hand side is a lot dimmer than the digit on the left. Now you can see some blinking in the camera, but that's not visible to the naked eye. But even the blinking looks different on the digit on the right, and if you look at it, if you look carefully, you notice that the digit on the right appears to be in an off state a lot more than the digit on the left. So it looks like the digit on the right is actually getting less on time, and that can only be a problem with the software that I've put onto the PIC that's controlling the little module. So I thought I'd take this as an opportunity to look at the software quickly and the IDE and the process of reprogramming one of these devices. Here's the program in the IDE. It seems very simple. What could be going wrong? Well, we read the input, we display the lower digit with a sleep, then we display the upper digit with a sleep. And we can see that when we run this program, we get two traces out of the logic analyzer. The red trace is the right-hand digit, the blue trace is the left-hand digit. Now remember, the displays are only turned on when these signals are low, so it's pretty obvious that the left-hand digit is low for about twice as long as the right-hand digit. Now in that situation, the left-hand digit is going to be about twice as bright as the right-hand digit. It's going to be on for twice as long. What's going on here though is that the upper digit is not only on for this sleep period, it's also on for the time it takes to read the next sample. And on these microcontrollers, everything takes a bit longer than you might expect. They're running at megahertz, not gigahertz. So if I want both displays to be on for the same amount of time, I need to make the lower digits stay on for a little bit longer. I could work out how long these delays take, but I'm not going to do that. I'm just going to copy that read operation and put it redundantly in the middle there. So we'll have a read and an update, a read and an update. Now if I run that in the simulator, let's see what the output looks like. Okay, the simulation is now running. If I stop it, I can then look at what the logic analyzer captured. Right, immediately we can see that the low phase for both of the signals is about the same length. So I'm pretty confident that's what's actually causing the problem, and I think we've solved it. So now that we've cured the problem, we need to take the hex file that was created by building the software, you can see the path there, and put it into another bit of software that Microchip provide called the IPE. That's the integrated programming environment, which is this piece of software here. You can see I've already got the path set up, and the first thing to do then is to get the chip out of the module and into the programmer. I'm using this programmer device here called the PIC Kit 3. It's very cheap. It's on eBay for about £5. There's the microcontroller wired up to the programmer device. So first thing to do is connect to the programmer. Okay, there we go. And then when it connects, hit program. Only takes a couple of seconds. There we are, that's done. And let's get the chip back out of the programmer and into the module, and let's just see what it looks like. Okay, put that to one side. Pop the chip back into the module. Okay, put the displays back in, and fingers crossed, both digits will be the same brightness. Okay, let's turn it on. Right, I appreciate that might be difficult to see. Let me see if I zoom in, it might be more obvious. But for sure, both those displays now look very similar. They're cycling very quickly through because I've got a fast running counter over here. But I can say visually it looks much better. So great, that's how you do it. You're programming a PIC using the debugger, using the logic analyzer. Thanks very much.